Alright, so we're talking about circular motion here, and a distinct memory I have from childhood is I had a younger sister, and so this is a drawing of my sister and myself in the back seat of the car, so mom and dad would be over here, and we lived in this place with a windy road, and so the car would be going around corners, and I remember we'd play corners, which is basically me torturing her, so playing corners. And what that meant is when we went around a corner, like depicted, I would squish her against the wall of the car. And it was really easy because we're going around a corner quickly, and it felt as if we were being thrown to the outside. So I'm going to write that. Felt as if we were being thrown to the outside of the corner. And you have probably experienced this. So the physics behind it is we weren't actually being thrown to the outside of the corner. If we look at, so here's a top view. Okay, here's the car, and we could say that the velocity is in this direction, and the corner is going like this. So what happens is, in order to, I'm going to draw something different. So here's the car, and here are my sister and I, and the corner is going like this. So both my sister and I are objects with mass, and so Newton's first law says that objects in motion tend to stay in uniform straight line motion, meaning my sister and her mass want to go in that direction, and me and my mass want to go in that direction, unless acted upon by an outside force. So what happens as the car goes around a corner is the car has to push us in this direction in order to get us to complete a circular path. And the direction in which it pushes us is always perpendicular to the path of the circle, or the tangential direction of motion at that point. So my sister was complaining, "Wow, you're squishing me." And the reality is that the car was pushing on her, which was pushing on me in order to move us into the circular path. So we talk about the difference between two words, and one is called centripetal and one is called centrifugal. I was kind of a nerd, and so at some point she'd be like, "Wow, you're squishing me," and I'd be like, "It's not me, it's the centrifugal force," because I learned these cool words. The reality is I was wrong, and so centripetal is, the root word is center seeking, or towards the center. And the reality is that this is the force that moves something in a circular path. Objects travel in straight lines unless acted upon by an outside force. So in order for something to move in a curved path, there has to be some force, and that force that moves it into the curved path is always going to be directed towards the center of the circle. If a force were directed tangentially, that would speed it up. But when we talk about a centripetal force, so this is the force that moves. Let me finish my sentence. An object, such as my sister or I, in a circular path. Okay, so centrifugal force, this is me as a little kid, it's the centrifugal force. So this feels like being pushed to the outside. To outside. And so gravity, it feels like we're being pushed downward, even though we're just standing still. If you were in an elevator being accelerated upward, you'd have this sensation of being pushed downward. And so this is similar. Because we're accelerating towards the center of the circle, it feels as if we're being pushed to the outside of the circle. So it feels like being pushed to outside, and we call this a fictitious force because it doesn't really exist. And let's see if I can spell fictitious. No idea. Fictitious force. Doesn't really exist, even though it sure feels like it. Okay, so there's my sister and I. And let me draw some specific stuff on this diagram. So this, at this instant, this would be the direction of the speed or velocity. Okay, sorry, direction of velocity. That's the vector quantity. And at that moment in time, the acceleration would be like this. Somewhere later on along the curved path. So these are velocity vectors. The acceleration towards the center of the circle, the acceleration towards the center of the circle, and the acceleration towards the center of the circle. And that's the way it goes. So this is a weird situation in which we can have something that is moving at a constant speed. If something's moving in a circular path, so we can say moving at constant speed. We can't technically say that it's moving at a constant velocity because the direction of the velocity is changing. And if the direction of the velocity is changing, we say that the velocity is changing. But if it's moving at a constant speed, yet accelerating. So this is our first instance of a situation in which something is accelerating, meaning its velocity is changing, but it's not speeding up or slowing down. And so we say it actually takes a force to change direction. Takes a force to change direction, and this is accelerating. Because the velocity, the direction of the velocity is changing. And you can picture yourself running around in a circle or driving in a circle or swinging something around. It takes force to do that, and that force is always directed towards the center. We're interested in that acceleration, and this is the formula we use. And so this right here is referred to as centripetal acceleration, A sub c. And this v technically is not velocity, this is tangential speed. And tangential is pretty much my favorite word because it just sounds so cool. So I try to use it whenever I can. So tangential speed, and this is the radius of the circular path. Okay, so I think we're going to do a couple example calculations on the next page. But first, let's see what else we have. Ah, yes. Okay, so we talked about difference between centripetal and centrifugal. And in these situations, because we have something moving in a circular path, sometimes we don't know how fast it's going, but I say it's useful to consider. So you know, and you've known this for a long time, that distance is rate times time, or speed is distance per time. And if an object is moving in a circular path, we know the distance around. In math, we call that the circumference, and we can calculate that by 2 pi r. And then the time to rotate around once, so this period of rotation, we're going to use this term frequently, period of rotation, so it's a period of time. We also use period of oscillation when we talk about simple harmonic motion soon. Anyway, so you can use this to find the speed of an object if you know the radius of its circular path and how long it takes to go around. So we could use this for, like it's kind of interesting to consider the speed of Earth around the sun. We're going pretty fast. Or if you're on the equator, right, the Earth is spinning, and how fast are you actually moving? You know, it's something like 1,000 miles an hour. It's pretty fast, even though we don't feel that. But you could use this to figure out how fast you're going. Okay, let's put that, no, let's keep going. We can do this like this. We have two examples, and I've solved them out here. So for our first example, we have a car, and it is moving 10 meters per second around a radius, around a curved path of radius 20 meters. And so this is about 60 feet. This is about 20 miles per hour. So imagine making a big loop in the parking lot, and you're going 20 miles an hour. That would be pretty fast. You're not supposed to drive that fast in the parking lot, but you can picture the situation. So here's a diagram. This is a top view. here's a diagram. This is sort of a 3D side view. This might be a little confusing because it almost looks like this is going, upside down, a loop-to-loop thing. But anyway, so diagram, given information, radius is 20 meters, speed 10 meters per second. I don't know where my little fraction marker went. And then we know these two things. The centripetal acceleration is v squared over r, and F equals ma sometimes is written like this: F sub c equals ma sub c, meaning centripetal force is mass times centripetal acceleration. So when we go to calculate the centripetal acceleration, whoops, I almost messed up there. We have the speed squared divided by the radius, so 5 meters per second squared. And the question is, well, does that make sense, or what kind of a value is that? It makes sense. 1g of acceleration, 9.8 meters per second squared. And so a normal car would kind of start to be sliding out at this point. But this is probably doable in a normal car. Okay, you'd need like a super Formula One race car, I think, to obtain an acceleration of 1g going around a corner. Otherwise, it would just slide out. Probably doable normal car. And of course, we're not talking about a snow, icy parking lot where you're drifting all over the place. Probably doable normal car. But that'd be pushing the limits. And then we're asked to find what force is necessary to pull the car into the circular path. So here's a free body diagram. We've got, and this is, I was trying to bring this 3D situation. So we're basically looking at, imagine looking at the car from the front as it moves around this circular path. So gravity pulls down on it, the road pushes up on it, and then there's friction between the road and the tires that moves it into its circular path. So using F equals ma, we know the centripetal acceleration, we know the mass, we get 5,000 newtons of force required to move the car into a circular path. And if you've driven on icy roads and tried to make turns, it's obvious that there is some force necessary, and sometimes ice doesn't really provide that friction. So the force of friction, notice how when this is moving around the circular path, the force of friction is equal to the centripetal force. It is the force of the road on the tires that allows you to make that turn. So that is 5,000 newtons. And when we're asked, well, what's the minimum coefficient of friction? We know this from last week and the week before, where the force of friction is provided by the stickiness of the surfaces and the force that pushes those two surfaces together. So in the case of our car, and I didn't have this written, the weight, mg, this is where that 9,800 newtons came from, is mass times acceleration due to gravity, and the car is not levitating and it's not sinking into the ground, meaning the normal force is equal to the weight. These forces balance. So we have frictional force mu times 9,800. Notice how this mu is not an m. And then when we divide, we get a coefficient of friction of about 0.5. So that's somewhat reasonable for dry pavement and car tires. Okay, next example shows this. So we're going to do a lab similar, or maybe you've already done the lab at this point. But the idea is, if you have a cup of water attached to a string, so there's water in here, we usually do this outside, you can spin it fast enough so that the water doesn't spill out. It's also possible to spin it slow enough so that the water does spill out and get all over you, but the goal is not to do that. So here's a water drop landing on the physics student who did not spin their cup fast enough. So what we're interested in this question is, well, how fast does it have to be going? And we're interested in the speed at the top of the path. How fast does it have to be going so that the water just doesn't spill? Because you could just spin it super, super fast, although the cup or the string might break. But it's sort of the unique challenge, how fast, so it just doesn't spill. Okay, so here's free body diagram. At the top of, when we have something moving in this loop-to-loop, at the top, the weight provides all of the centripetal force. So when you're spinning this thing around, you can feel the tension in the string basically go to zero. And then you have to really pull, and then the tension's zero. And then you really have to pull, and then the tension's zero. So notice how there's no tension drawn in here. The weight provides the necessary centripetal force. However, down below, the tension is very large relative to the weight because the tension has to provide the centripetal force plus balance out the weight. So I say at the bottom that tension minus weight is going to equal centripetal force. And so if this moved at a constant speed, which when you're spinning the cup of water isn't much of a reality because it kind of speeds up and slows down. But if this were moving at a constant speed, then down here the tension would have to be twice the weight, and up here the tension would be zero, and the centripetal force would be equal to the weight as it moves around. All right, so this is sort of a general truth. At the top of the swing, it will just make it, meaning not spill the water on you, if the tension is reduced to zero. The weight provides the exact centripetal force to create that circular path. So here's the top, here's our free body diagram. We say that weight equals centripetal force, and we just plug in, given our what we know these things are. So we know that weight is mass times g, acceleration due to gravity, and we know that centripetal force from F equals ma is mass times centripetal acceleration, where centripetal acceleration is v squared over r. So notice how the masses cancel out. This happens frequently in physics. Galileo, Leaning Tower of Pisa. Here's the Leaning Tower of Pisa. And he dropped the big object and the small object. And people said, "You fool! The big one is heavier, it'll fall faster." But he proved them wrong. So the masses cancel. We end up with this, and multiplying by r and taking the square root gives us that the speed at the top of the path would have to be square root of g times r. And let's see, I think in that example, radius was 1, so it would be the square root of 9.8. And my calculator says, we don't know. Let's clear that. Yeah, 3.1 meters per second. So that sounds reasonable. That'd be like 6 or 7 miles an hour. So we will experiment with this.